Hi, let's learn how to design arithmetic circuits, including adder and subtractor. What is iterative circuit? Iterative circuit form repeated operation using a basic unit repeated across multiple stages. So normally they are used to handle complex tasks by breaking them into smaller, manageable parts, optimizing performance and scalability. These circuits are advantageous for simplifying digital system design. Why? For this kind of design, we just design one slice circuit, and then we just need to duplicate them several times or n times to implement n-bit circuit. Adders is one of the example. You just need to design one bit full adder and then multiply or instantiate them multiple times to expand it into n-bit adder. Let's look at how to design one bit full adder. First, you have a truth table, and the inputs include input x, input y, and carry in, and it will produce sum and carry out. So 0 plus 1 plus 0 equal to sum 1 and no carry. 1 plus 1 plus 1, for example, with sum 1 and carry out 1. To know what gates compose the one bit full adder, you can solve the truth table using Carnot map as shown here. So after solving, you see that sum can be implemented using x XOR y and XOR carry in, whereas for carry out can be implemented using sum of products of xy, x carry in and y carry in, as shown here as a two-level or two-stage AND OR gates. Or you can just rearrange the lateral to get a slightly different solution where it consists of slightly different gates. So this circuit represents logic for sum, and this for logic carry. So you can use schematic method to design the one bit full adder, or we can use the hardware description language, the Verilog, to design. So this is more common method in industry. Okay, and first you declare the input output. So input output, the more practical or recommended way to declare input output using small or lowercase or small letter. Okay, x, y carry in, s and carry out, because in Verilog, uppercase normally used to describe parameters or constant. So XOR, you can use this assign statement, and for sum of product, you can use this assign statement. So when we want to expand this design into multiple bits, you can, as mentioned earlier, instantiate or duplicate the same design for n times, in this case 4 times, to build the 4-bit adder. And after duplication of the module, we have 4 instances, and they are connected such that the first carry out is connected to the second carry in. The second carry out is connected to the third carry in, and so on. So the adder that is handling the least significant bit, addition of the least significant bit, is called LSB adder. And for carry in of the LSB adder, normally we just set the carry in of C0 to 0. Due to the cascading connection, the speed of the circuit is limited by the propagation of the carry signal from C0 to C1 and so on. However, we have advantages of using this adder where it is easier to implement, smaller and lower power. So we call this adder ripple carry adder because of the characteristic where the carry signal form a propagation path from carry in to carry out of the MSB adder. But it still works well for the smaller adder such as 4-bit adder, 8-bit adder and so on. And moreover, the full adder or this ripple carry adder are often used as a basic building block for more advanced adder. So let's look at the computation, the animation here to show that the carry propagation path dominate the delays of the circuit, where the adder, say the second adder, need to wait for the carry coming from the first adder before it can complete the value for sum and so on. You can add the extra XOR here to detect the overflow. If you have two numbers, x plus y, where x consists of 4 bits and y also consists of 4 bits, When overflow happens, the answer computed here are not valid and cannot be used. So this XOR logic, which connect the MSB carry in and the MSB carry out, is very important to tell overflow happen or not. Okay, let's look at how to expand a single bit full adder into 4-bit adders. So this block shows the module of the 1-bit adder we designed earlier. So note that the input, X, Y, and carry in as shown in this diagram, and the output is sum and carry out. So we expand the circuit, the full adder, we instantiate for 4 times. So the first instance, when we want to write in our top level module, we write the name of the module name followed by the instance name. So you can see here there are 4 times module names is written to show that there are 4 times of instantiation to call or we build the 4-bit adder here, and we put a different instance name for each instance so that compiler can differentiate there are 4 different instances. But note that these instances coming or based on the same design, which is 1-bit full adder. Okay. By the way, before the 4 instances are stated or described in the top level design, as usual, we need to declare the input and the output. So the input in this case is X, Y, and carry in. So for X, there are 4 bits because it's for 4-bit adder, bit 3 down to bit 0. So you can use the vector to describe the 4-bit bars or the 4-bit input for X and Y. Carry in is 1 bit only, so you don't need the vector. And for output, there are 4-bit sum and a single bit carry out. So apart from inputs port and output port, we also need to declare the wire. So the internal wire consists of C1, C2, C3. But to make the description of the 4-bit adder in an iterative or array form, we can declare also wire using vector and with the bit starting from bit 0. Okay. So we can see in this illustration, bit 0, C0 is actually the carry-in of the LSB adder. Bit 1 is actually the carry-in of the second adder. Bit 2 is the carry-in of the third adder, and so on. And C1 is the carry out of the first adder, C2 is a carry out of the second adder, and so on. So carry in is can be declared in the array or vector form, which start from bit 0 to bit 4. So we can use wire, declare the 5 bits vector, and name it C. So for input and output, C0 is declared as a wire, and at the same time it is also an input. C4 is declared as a wire, at the same time is the output port. So we need to use the assign statement to show the connection of the wire to the port. So for C0, we can use assign C0 to carry in. So why we put C0 at the left hand side? Because it's the carry in that supply the signal to the C0. And for the output, we use another assign statement to assign C out equal to C4. Okay, so where the wire C4 supply the signal to the C out. So back to the instances of the full adder 1-bit. After we write the instance name, it will be followed by a bracket. So inside the bracket, we need to show the connection of the top level signals to the input-output ports of the components or instances. Okay. So for port connection, there are 2 methods. The first method is port connection by ordering. It means you connect the signal, okay, you put the signals of the top level circuit in the ordering, which is the same as the order you define in the submodule. So in the submodule full adder 1-bit, you declare X first, followed by Y, followed by carry in. So at your top level circuit, you want to connect X0 to port X, Y0 to port Y, and carry in or C0 to C in. So you need to put in the right order where you put X0 first. Why? Because in the submodule, the port X is declared first. So if you put X0, the top level signal here first, that means you connect X0 to port X, X0 to port X, and Y0 to port Y, Y0 to port Y. Similar things you do for the following instances also. So you after complete the signals connection to the components or instances, then you complete the description for your top level circuit. As mentioned, the port connection can be done by ordering, and the second method of port connection is called port connection by name. Okay? So this, if using this method, when you want to connect the top level signals to the input output ports of the components, you need to, as the name tells here, you need to write the port name first. Okay? So for example, here you write the port name Cin. Okay, port name is written inside the block of the instance. Cin, write the name Cin first. Dot Cin. So this dot Cin refer to the port name of Cin. And in the bracket, put the top level signal you want to connect to that port. So the first instance will connect the C0 to port Cin. So you write the port name first, dot Cin, connect to top level signal C0. Dot X, the port X will connect to top level signal X0. Port Y to Y0, port S to S0, and port C out to C1. Okay, do the same for the following instances. So this way is called port connection by name, okay, because you write out the name of the port first, followed by the top level signal you want to connect to that port. So this method, though a bit longer in terms of describing the instance, as you can see, we need to type the port name every time before we put in the top level signal. But it has the advantage where you don't need to follow the ordering you define earlier or you declare earlier in the sub module. Okay, so just now we talked about 4-bit adder. If next time we want to expand the design to 16 bits, so it seems that we need to repetitively type the full adder or instantiate the same full adder for 16 times. If you want to expand it 32 bits, then you have to list out all the 32 instances. Coding like this may be prone to errors because you need to type many times, and it's also harder to modify and to scale, especially for the bigger adder. So we have the solution. Instead of repetitively type the instances of the full adders, you can use generate block. We can use the syntax or the construct generate block in the Verilog as shown here. So using generate block, you can write the for loop and to ask the compiler to help you to generate the multiple lines of the instances. So how to do that? First, because normally in for loop we need the iterator I to tell how many times the compiler need to generate. So first we need to use the genbar keyword to declare the integer or iterator I that will be used in the for loop. Then you start the generate block with the keyword generate, and don't forget to end it with end generate. So inside the generate block, write the for loop, iterator I, and how many times you want the compiler to repetitively print or include the instances in the top level design. So in this case, we have I up to 16 because we want the compiler to print or to instantiate the full adder 1 bit for 16 times. And you utilize the I, the iterator, to describe the top level signals. Now you see the reason why we want, when describe or declare the input output and even the wire, we want the signal to be in the vector or in the iterative form, so that we can use this array way to describe the one line full adder here using iterator I. So for first iteration, the compiler will generate full LSB full adder that connect X0, Y0, C0, the carry in, and S0, the sum, and C1, which is the carry out. In the second iteration, the compiler will generate full adder X1, Y1, connect to the port X and Y, and C1 to the carry in. S1 is the sum, and C2 is the carry out. So this saves a lot of effort. So generate block, as you can see, is very useful when you want to describe top level module of an iterative circuit. One thing which is very important is don't forget to give a name to the for loop. This is especially important because some compiler will produce error message if you don't name the for loop. So how to name the for loop? After you describe the for loop and start it with begin, put the column and put the name for the for loop. Okay, in this case at stage. Okay, and then don't forget to put the end after the for loop statement. Okay, so now you just need to declare less, to write less lines compared to 16 repetitive instantiation line. To make the coding even more flexible and reusable, we can instead of putting the upper bound like 16 minus 1, putting the upper bound in the vector, you can use a symbol to represent the upper bound. And you can symbol n, which is a constant or parameter, need to be first declared after the name of the module. After the name of the module, put a hash in the bracket, declare the parameter n and equal to the default value 16. Then in the vector, instead of using 15, you can just use n to describe the upper bound of the vector and also the upper bound of the iterator. So why I said this will make the code more flexible and reusable. When you next time want to reuse this for this adder for other design, and other design need the adder to be of different size, for example 32 bits, then you just need to modify this parameter n equal to 32, and you don't need to change anything in the content of the module. Or let's say this adder, bigger adder, will be used in some top level design. You can let this 16 as a default value here without any modification. But when you instantiate this adder, you can change the default value of the n. So for example, you after instantiate it, put a hash in the bracket dot n, the parameter n, and then in the bracket tell the size of the adder you want to use in this top level design or some test bench. Okay, so if you put 32, that means that for this particular design, n will be overwritten as 32. Okay, that is about how to design the adder, single bit adder, and how to expand it into n-bit adder. Now let's look at how to modify an adder to become a subtractor. So you may ask, why not just using a subtractor which is designed from its truth table with borrow signals and so on. So the reason we there are two reasons why we use the adder as a base circuit to be modified into subtractor. One reason is this kind of subtractor will have less gates compared to the purpose built subtractor, the subtractor that you purposely built based on its truth table. Okay, that is the first reason, less gates. The second reason is because normally in a circuit, it will not just have a subtractor alone. Normally the circuit which has a subtractor will also need adder. So if we can see the similarity between the subtractor circuit and the adder circuit, then we can easily accept the fact that the adders can share a lot of logic with subtractor. So these two designs can be merged and make it a configurable design, a circuit that can be configured between addition function and subtraction function. So let's see why they can share a lot of circuits, a lot of logic. Because as you learned earlier, the subtraction x minus y can be described into an addition problem where x minus y is actually x plus negative y. So this negative y here can be implemented in digital circuit as a 2's complement, where we invert each bit in y and then plus 1 as shown here. Okay? X minus y is actually x plus negative y, and the negative y can be represented with inverted y plus 1, which is the 2's complement. So from here you can see that we can modify a full adder, a 4-bit full adder, by first putting the inverter after each y signal to get the inverted y, and then we fix the 1 here. Okay, at the LSB adder you need a 1 here. That can be done by fixing the 1 to the carry in of the LSB adder. However, doing such modification will forever or permanently modify the circuit to subtractor. In other words, the whole circuit can perform only the subtraction function. So this is not normally we need in the circuit. As mentioned, a circuit that has a subtractor may normally also have the adder. So it's more practical to have a circuit that consists of full adders, but we make it configurable, where at the first case it can consider a plus original b, okay? A plus b, which is actually the addition function, and in the second case or second mode, it will perform or bring in a and b bar, which it will perform the subtraction, a plus b bar, and with the plus 1 at the LSB circuit. So you can do that, realize that configurability configurability by using the 2-to-1 multiplexer, where the multiplexer will select between B and B bar depending on the mode of the circuit. And the mode signal of the circuit can come from the carry-in of the LSB adder. Because the carry-in, when 0, it will perform addition. When 1, it will perform subtraction. During addition, the carry-in will take 0, so the carry-in will take 0. That also means there is no +1 at the LSB adder. At the same time, because the carry-in also play the role of the select signal for multiplexer, so original B will pass through the multiplexer to the full adder, so it will just perform the addition. Whereas when it is switched to subtraction, then the carry-in of the LSB will be set to 1, and this one is important because for the +1 at the LSB stage here, and this one also instruct the multiplexer to select all the inverted B to the full adder so that it can do the +B bar here in the full adder. So we saw the whole process, we will realize the subtraction process. So instead of multiplexer, the alternative design will use the XOR to where it also connect to the mode signal to control when to invert the B, when to take in the original B. Because XOR with 2 inputs, one of the inputs can be a control input that determine the XOR output will be the inversion or original value of the other input to the XOR. When S, the second input of the XOR, is 1, then it will invert the input value, the other input value, and propagate to the output. So as shown here, when 0, then XOR will just pass the original B to the full adder. When 1, it will invert the B and send to the full adder. The control signal also connect to the carry-in so that it realize the +1 at the LSB stage when subtraction happens. So one good thing using XOR is, in terms of circuit layout, XOR is more compact or slightly smaller than the multiplexer. Okay, so this is the ripple carry adder that is composed by using 2 half adders. So just now, I briefly mentioned that one of the limitations of using multiple bit ripple carry adder is that there is a propagation path, a long propagation path that involves the carry signals from one adder to the next adder. So how this propagation path happen and affect the performance of the multiple bit ripple carry adder? Let's look at the delay analysis. So let's assume one XOR gate causes 2 delays while the AND gate or OR gate has 1 delay. So when signal propagates through the XY signal propagates through the XOR gate, it will take 2 units of delay and 1 more XOR gate on the way, and it totally takes 4 delays to form the signal S. Same also goes to the carry out, where the XY signal go through this XOR, which has 2 delays, and go through the AND gate, where it accumulates to 3 delays, and finally go through this OR gate and accumulate to 4 delays before the carry out signal is formed. So when you have multiple full adders cascaded, then it ends up the delay as long as 2n plus 2, where n is the number of adders. So if you have 4-bit adder, then the delays that will be incurred in the design is 2 times 4 plus 2, which is 10 delays. So that means the more number of bits, the delay will increase. So that is the reason why just now I said the limitation is caused by the propagation delay for the carry signal from this carry in to the carry out, and it doesn't end as the output like S, but this carry out will be connected to the next carry in to produce the following signals. As you can see here, let's take a note at how the signal propagates from C0 to C1 and so on to produce the following signal like sum and the next carry out. And take note also, because X3, Y3 down to X0, Y0, they are input signal provided from the beginning, so the 4-bit signal will go into the circuit simultaneously. However, when it goes halfway, you need to wait for the carry signal to join before they can complete to produce the output signal. Okay, 2 delays, and then another 2 delays to the carry out. And you can see here the signal stop here, and sorry, the signal is not complete here until the carry in come in to form the final signal for the carry out and sum. So that's why the total delay is mainly determined by the carry signals, how long the carry signal takes to join the X and Y to produce sum and carry out. That's how 2n plus 2 delays are derived, and it does show that the delay will become longer when the number of bits for the adder is increased. Look at the circuit again, but this time we partition the circuit so that we can introduce some new terms here called carry propagate and carry generate. P carry propagate and G carry generate. Okay, so this is again a 4-bit ripple carry adder, and each unit of adder is composed of these 2 half adder. Okay, and we put that means that this is the one full adder, the third bit full adder, and the last bit full adder. But we partition the circuit such that the 2 XOR and the first AND gate is put in this block. Okay, the 2 XOR and the AND gate is put in this block we call partial full adder. And the remaining AND gate and OR gate we put outside here. Okay, the reason we partition the circuit like that is to show the propagation path here that is connected. Okay, and that form the long delay, the 2n plus 2 delay to get the final carry out. Okay. So that's the reason why we partition circuit like that, so that you can see that ripple or that propagation path. Besides that, we also want to introduce the new term called carry propagate and carry generate. So the signal that comes from bit A XOR B, okay, this A XOR B, and this point of signal, this signal we call carry propagate, and we denote it with E, and another which is carry generate actually come from the A and B logic. This one we call it carry generate. So each block here got carry propagate and carry generate, B and G. Carry propagate, carry generate. Okay. So later we will use these symbols to discuss the another adder called carry look ahead, and how the carry look ahead perform better compared to ripple carry adder. So just now you have seen the long propagation path. Okay, the reason the carry ripple along the propagation path is because the cascading of the LSB adder to the next adder and so on, that create the dependence of the carry signals. In other words, the carry signal for the second adder depends on the carry signal of the LSB adder. Carry signal of the third adder depends on the carry signal of the second adder and the LSB adder. That creates the long propagation due to the dependence of the signal. So now let's look at how the carry look ahead adder, this is another adder, carry look ahead adder, how the carry look ahead adder helps to overcome the limitation of the ripple carry adder. So remember the signal called carry generate and carry propagate. So let's look at again the Boolean expression for sum and carry out. Sum is A XOR B XOR C. You can see here A XOR B and then XOR C. So this is a sum Boolean expression. And we introduced the middle signal here, carry propagate, which is denoted as P. So let's put the P signal to replace the A XOR B. And look at the Boolean expression for carry out, which is the AB or AC or BC. And we replace the AB with the carry generate symbol. Okay. We arrange this sum of product, we get AB, okay, or A or BC, and then using the Boolean laws we have, then we can rewrite the C out Boolean expression to AB or A XOR B C. Okay, so from here you see the carry out can be described using carry generate and carry propagate. Okay, so this further this red lines is just to show that from A or B, it can be expanded to A, B bar, or A bar B, or A and B. And this AB here can be simplified to just AB. That's why the remaining AB bar or A bar B will be written as A XOR B. So let's use the same expression to describe the C out for the first C out for the first adder, okay, and C out for the second adder, C out for the third adder, and so on. So let's use the new symbol carry generate and carry propagate to describe the carry out of each adder. So again, I would like to show the dependence of the signal. So from this Boolean expression, you can see that C1, you can see that the carry out of the second adder depends on the carry out of the first adder, which is this. And carry out of the third adder depends on carry out of the second adder. The dependence here that create the long propagation path. So if we rewrite the Boolean expression using the symbol G and P, so for the second carry out, just replace this C1 with the C1 Boolean equation. So it becomes G1 or P1 G0 or P1 P0 C0. Do the same for the following carry out C3, which originally depends on C2, but replace the C2 here with the Boolean expression in terms of P and G. Okay. If you write so, then now you look at all the carry out Boolean expression, you'll now see that the carry out depends on the carry generate, carry propagate, and the C0 only. Okay, look at the last carry out. C4 is determined by P, G, and C0 only. So in other words, if you implement the logic for carry out based on the new Boolean expression here, you break or eliminate the dependence of the C4 to C3, C3 to C3 on C2, and C2 on C1, and so on. So you eliminate the dependence of the carry out of the given adder on its previous carry out of the preceding adder. So you have eliminated the dependence, and in other words, it breaks that long propagation path. Okay. So let's look at the new logic that is built based on the newly derived Boolean expression for this carry loop ahead adder. So you see here, let's look at the effect. The difference can be seen from the logic of the second adder. The first adder is still the same. The difference can be seen from the logic of the second adder and onwards. So you see here now, to produce C2 no more depends on C1. We have break the dependence because C2 just need the carry generate of the adders, carry generate G1 P1, G0 P0, and C0. So you see C2 just need to depend on G1 P1, G0 P0, and C0. Let's look at C3. C3 no more dependence on the C2. It only depends on the G, P, and C0. In other words, actually, some of you may have noticed, by using the new Boolean expression, now we make the generation of the carry out signal as a parallel process, where it read in the A and B that generate G and B, which are read in a parallel, and get the C out signal faster. And you can see also, by having the advantage from the parallel logic, the small trade-off is that more logics are needed to make the parallel happen, so that the carry out can be generated in a shorter time. And you can see that instead of 2n plus 2, now the carry out will come up or will be generated after 4 delays. The triangle indicates the delay. So all the carry out will come out almost at the same time, which is after 4 delays. And the C3 after 4 delays, C3 will be generated, and it will take 2 more delays to generate the sum signal. That's why to finalize a sum signal will take 6 delays only. That means no matter how many bits of the adder you build for carry loop ahead adder, you just need 6 delays. No more depending on the number of stages. Let's look at the last type of adder called carry select adder. Carry select adder will use redundant hardware to make the calculation faster. So what is mean by redundant hardware? Let's say you want to implement 8-bit adder. So you split the adder into two, the lower 4-bit and the upper 4-bit. And these two adders are implemented by two separate set of 4-bit adder. Let's assume this 4-bit adder is carry look ahead adder. So it takes, as shown earlier, it takes 6 delays to compute everything. Okay, so that's why we put here 6 delays. So the first 4-bit adder here, which is carry look ahead adder, is to compute the lower 4 bits of the numbers to produce S0, S1, S2, S3. The upper 4 bits is implemented by a pair of adder, and where one of the adder we assume carry in 0 coming from the lower 4 bit, and the second 4 bit adder we assume there's a carry equal to 1 coming from the lower 4 bit summation. So by such assumption, by having the redundant hardware here means the extra hardware. By having extra hardware, we can start the upper 4-bit addition earlier. So this upper 4-bit doesn't need to wait for the completion of the lower 4-bit. It can start at the same time as this lower 4-bit adder, because it has two sets. One is considering no carry out from the lower 4-bit, the other with carry. So these three adders we can perform or start operation at the same time. Each of them produce a summation. Of course, this S3 down to S0 confirm correct. However, for the S7 to S4, it has two set of answer. One S7, S4 come from this the top adder here, and another S7 down to S4 come from the bottom adder here. And the multiplexer will choose the right answer. Okay, it will choose the answer from the right adder based on the result of C4 from the lower 4-bit adder after 6 delays later. Okay, so if this result of C4 from the lower 4-bit say that there is no carry coming from it, then the multiplexer will select the answer that is computed earlier, the S7 down to 4. It will select the S7 down to 4 from the top adder, because the top adder assume no carry in. Otherwise, it will take the bottom adder answer. Okay, so C8 is the final carry out, so it also need to be selected based on the C4. Okay, C4. If C4 is 0, then this C8 will be passed as a final carry out. If C4 is 1, then C8 of the bottom adder will be passed as the final carry out. Okay, that's all. Thank you for listening to this video lecture.